Section 5.5, the substitution rule. In this section, we will use substitution as a tool to use the chain rule backwards. So chain rule occurs in situations where you have composition of functions. That comes up a lot when we're trying to calculate integrals. So let's look at an example and see what our strategy is going to be. So first of all, we're just going to try using trial and error to determine the integral of 2x plus 1 to the fifth with respect to x. Trial and error meaning we're just going to go for it. Why are we talking about the chain rule here? Well, because we have a function inside of another function. So we have 2x plus 1 inside of a fifth power. So in the spirit of the chain rule, I'm going to work on the outside function part first. So I'm going to focus on the fifth power portion. And I'm going to try to just apply the power rule to this. So I'm going to take that 2x plus 1, apply the power rule, and add 1 to the power, and divide by the new power. And then I'm going to go over here off to the side, and I'm going to try and take the derivative of that to see if it gets me back to where I started. So I'm going to take 2x plus 1 to the sixth over 6, and we're going to take the derivative. No need to use the quotient rule. That over 6 is just like a constant of 1/6 out front, so we can just ignore that part. So how would the power rule work here? We would take the 6 and bring it down. The 2x plus 1, we would subtract 1 from the power, so that'd be a 5. The over 6 would just sit there. But then the chain rule would kick in. And because the inside portion is 2x plus 1, we would multiply by the derivative of that and have times 2. So now let's see, did that get us back to where we started? So these 6's would cancel, which is the usefulness of the power rule, but we would have this extra 2 over here on the right that isn't canceling. And if that 2 doesn't cancel, we don't get back to where we started. All right, so what would cancel a times 2? How about if we came back over here and did a times 1/2? And then if we did that over here as well, so we had this times 1/2, that would be a 2 here, and then those 2's would cancel, and then when all of that cancels, we're back to where we started. All right, so it looks like that probably is the answer. To make sure I get the whole class of antiderivatives, I would add a plus c. And then let's go ahead and get rid of this checking our work stuff on the side and use that space to simplify our answer. All right, so not much simplifying that we need to do. We have the 2x plus 1 raised to the sixth. And the only simplification I really need to do is we have that 6 times 2 in the denominator, so I'll make that over 12 plus c. I'll leave it to you to go ahead and take the derivative of that and see that you get the inside of the integral back as a check on your work. But I don't want to have to do problems like this all the time where I'm wrestling with it to get an antiderivative. I want to come up with more of a concrete procedure I can use, and that's where substitution comes in. So we're going to try that exact same problem again, integrating 2x plus 1, that quantity to the fifth with respect to x, but this time using a substitution where u equals 2x plus 1. All right, so if I took this piece right here, u equals 2x plus 1, I could substitute in right there. And if I did that, that would be the integral of now u to the fifth with respect to x. And this is a no-no here. We are not supposed to have two different variables like this in our integral. If we're going to make a substitution and change from x to u, we need to completely change from x to u. So we don't want that dx there. So how are we going to get rid of it? So let's come over here and look at our substitution u equals 2x plus 1. And let's take the derivative of that with respect to x. So we're going to take the derivative of our new function u with respect to x. So on the other side, you take the derivative, you just get a 2. And now what we're going to do is, even though du dx is just a notation, not really a fraction, we're going to go ahead and treat it like it was a fraction for a moment and say, what if I multiplied both sides by dx and thought about these canceling like as if it was a fraction? If I did that, I would have du equals 2 times dx, and that would allow me to get rid of this dx. If I divided both sides by 2, I would have the dx by itself. So dx would be equal to 1/2 times du. And if I have that, I could get rid of this piece. So not supposed to mix the u's and x's together, so I'm going to destroy the evidence there, get rid of that, and go back and try and make a complete transformation of variables here. We use the u substitution to get rid of this inside piece, change it to a u, make that u to the fifth. Now we're going to replace this dx by 1/2 du. So my variable has completely switched from x to u. And now let's see what happens if we just continue on with this new integral we've set up. We can factor the 1/2 out front and then just have u to the fifth du. We can apply the power rule. So this becomes u to the sixth over 6. We would add our constant of integration c. That gives us u to the sixth over 12 plus c. Now the problem is we got asked a question about x's, and currently I'm trying to give an answer that has u's in it. So what I have to do is back substitute. So I take this and I say, well, wait a minute, we know what u is. U is 2x plus 1, so let's plug that 2x plus 1 back in there. And if I do that, I get 2x plus 1 to the sixth divided by 6 plus c. Notice that's the same answer that we got above when we just kind of wrestled with it. The other thing that you might notice is we did a lot more work. So I think it's reasonable to wonder, like, why would we want to go through all this extra work to do a problem that we did in just a couple lines above? And the main reason for now is that the one that we did above and the one we did here is kind of a simple one to figure out. We're going to see lots of them as we continue through the section that are a lot harder to just wrestle with and come up with a solution for. So if we can have a step-by-step procedure, we'll be able to do the easy ones like the one above, but we'll also be able to do the messy ones that probably would have stumped us if we were just trying to do it through trial and error process. All right, let's go ahead and kind of cement this procedure and make a list of steps that we're going to go through when we try to use substitution to integrate. So step 1, choose a substitution u equals some function of x that simplifies the original function. That u equals g of x is often some inside function. So I have that in quotes. So what do I mean by an inside function? Well, if you go back and you look at the problem that we started off with, 2x plus 1 was inside of a fifth power function. So we let u equal the 2x plus 1 part that was inside. Once you've picked your u, now you want to find du, which is equal to g prime of x dx. We kind of did that as a du dx first, and then we moved the dx over. But what we'll do in general is just say that when you have a u equals, you get your du by taking the derivative times the dx. So we won't do that like multiply by dx step because that's not official. That was just kind of thinking of it that way. This is our definition of differentials from the previous chapter. All right, let's go ahead and see what we do next. Rewrite the integral in terms of u and du. No x or dx should remain in the integral. So it needs to be a complete switch of variables. I temporarily wrote one with a u and a dx mixed together, but we're really not supposed to do that. If we change variables, it needs to be a complete change. So I'll show you as we go through future examples how to make sure you get it all cleaned up at once. Once you've made the substitution, integrate. If you try to integrate and you can't, it may mean that you didn't get the correct substitution. So try another substitution, see if you could pick some other inside sort of function. And then it's also important to know substitution doesn't solve every situation. So there's going to be more and more techniques of integration coming up, not just in Math 1, but also in Math 2. So substitution, though, will help us through a lot of situations. And then the final step is to back substitute. You're going to have an answer in step 3 that's in terms of u, even though the original question was in terms of x, so your final answer should be in terms of x. And really, of course, we mean there the final answer should be in terms of whatever the original variable was. It might have been a t or a y or whatever, but you need to get back to your original variable. All right, and then just kind of a quick box version and summary. If you let u equal g of x, where g prime of x is continuous on an interval, and you let f be continuous on the range of g, then if you're taking the integral of f of g of x times g prime of x dx, that can be converted to f of u du through the substitution u equals g of x. That's very complicated to read, but like if you look at what happened, here we have one function inside of another, and we let u be that inside function. And then when you clean up the dx, you're going to say du equals g prime of x dx, so that kind of is the rest of the substitution. All right, let's go ahead and turn the page and look at some examples of carrying this out so we can start getting more comfortable with the process. All right, let's get some practice with this new substitution strategy. So we're going to find the integral of x cubed times 2 plus x to the fourth raised to the fifth with respect to x. So given this strategy, we should let u be the inside piece. So the inside piece is what's inside of the fifth power, which would be this 2 plus x to the fourth. So let's let u equal 2 plus x to the fourth. And then to try and clean up the leftovers, we want to find du. Du is the derivative of this times dx. So derivative of 2 is 0, derivative of x to the fourth is 4x to the third. And then again, when you're finding du, and you do the derivative of your u function, you have to tack on the dx. All right, so let's kind of look at if we substituted, what would we have taken care of? So I already showed you in yellow, if we do this piece, we clean up the inside. So what would be left over? The x cubed and the dx. Well, good news. There's x cubed and dx right there. So what we want to do is solve for those pieces in our differential statement. So to get the green part by itself, we can divide both sides by 4. Those 4's cancel, and we can see that x cubed times dx is equal to du over 4. So we can substitute for the x cubed dx, du over 4, and we'll make a complete transition of variables. So let's see what this looks like. So this becomes the integral of u to the fifth, and then x cubed dx becomes du over 4. And what we usually do with the over 4, if it's just a constant, is just factor that out front as a 1/4. So let's see the two pieces. So there's our u equals 2 plus x to the fourth. We substituted in for that. The 5, which was the outside function, just stayed there. And then the x cubed dx became du over 4, and there's our du over 4 with the 1/4 factored out front. All right, now, in terms of this new variable, we have a very simple antiderivative because it's just a power rule. So we do u to the 6th divided by 6 plus c. So we get u to the 6th over 24 plus c. And all seems great and done because we're finished integrating, right? But we do have the wrong variable. So we need to now go back, substitute the u back in, and say this is 2 plus x to the fourth raised to the 6th divided by 24 plus c. And that's going to be my answer for this one. Since we're new at the process, we'll go ahead and check this answer by taking a derivative real quick. So let's go ahead and do that. If you take the derivative of what I've just shaded in green, you'd start with the outside portion. So you'd bring the 6 down, subtract 1 from the power, so that'd be a 5. The over 24 part would just sit there. Then you would multiply by the derivative of the inside, which would be 4x to the third, and the derivative of the constant would be 0. And if you go through and look at what cancels, this 6 and 4 become 24, which cancels the 24 on the bottom. You look at what's left inside, you have x cubed, which is right there, and you have 2 plus x to the fourth raised to the fifth, which is the other piece. So when we think we've found an answer and we find its derivative and it's the inside of the original integral, that shows that our answer is correct. All right, let's get this part out of the way and move on to the next one. So let's try and find the integral of x over x squared plus 1 squared with respect to x. And we do the substitution work underneath this time, so let's let u be the inside function. So the inside function to me looks like this part because that's getting squared, so it's inside of a square function. So let's let u be that. So u is x squared plus 1. It's important to notice I don't let u be x squared plus 1 all squared. I just want the inside piece, not the whole inside and outside piece together. And then du would be the derivative of this, which is 2x times dx. All right, so let's look at what's left after I do the initial substitution. I still would have this x and that dx right there. There's the x, there's the dx. I've got an extra 2, so I'm just going to divide both sides by 2 to get rid of that extra piece, and then go up here and try and do the substitution. So in the bottom, I'm going to have u squared, and then the green part, x dx, is du over 2, so I'll put a du here. I'll put the over 2 as a 1/2 out front. Since I have nothing in my numerator, I'll just put a 1 up there to make sure I have a placeholder. Much cleaned up looking integral compared to what we had a minute ago. This looks like a much easier one to find the antiderivative of. So keep that 1/2. I'll rewrite that as u to the -2, so the power rule applies. I then have the 1/2 times u to the add 1, divide by the new power, plus a constant. So what do we end up with there? Factor that negative from the denominator out front. We have -1/2. The u to the -1, we can make 1 over u. And then we have the plus c. And then finally we have the issue of our variable is not correct. We started out with a question about x. Right now we've got an answer in terms of u. So I back substitute, and for that back substitution, we're just going back to this. U equals x squared plus 1, so we'll substitute that in place of the u right there. So I have -1 over 2 times u, but u is x squared plus 1. Sorry, said the right thing, wrote the wrong thing. X squared plus 1 plus c. And there's our final answer to this one. I'm just going to highlight it. I'll leave it up to you to check this one if you want to with the derivative. Just a quick mention, in order to check it, you could use the quotient rule, but what would be better is to bring the x squared plus 1 up to the numerator as an x to the -1 power, so you could apply the chain rule right away. All right, let's go ahead and look at another one. So in this one, we have the integral of sine to the 5th x cosine of x. One thing that'll help us see what we need to do a little better here, I wouldn't normally write this because I'm used to this, and maybe some of you don't need it either, but I'm going to write sine 5th to the x as what it really is, which is sine of x raised to the 5th power. If I do that, I think it makes it a little bit more obvious that the inside function is this sine of x, which is being raised to the 5th. So I'm going to come down here and do my substitution scratch work and say I'm going to let u equal the inside function sine of x. Du would then be the derivative of that, so the derivative of sine is cosine, and then times dx. In this case, we get a kind of perfect substitution in the sense that after we substitute u equals sine of x and get a u to the 5th, the leftover pieces would be this cosine of x dx, which is exactly what our du is equal to. So that's kind of as clean as it gets in terms of substitution. So this becomes the integral of u to the 5th, and then again the cosine x dx just becomes du. So then I can apply the power rule, u to the 6 over 6 plus c, and then I can back substitute and have sine to the 6th over 6 plus c. So there's something that looked like a very messy integral to evaluate, but when I did the substitution, I end up seeing that it's just a simple power rule problem, just a u to the 5th. All right, let's go ahead and look at some more on the next page. All right, now they want us to find the integral of x over the square root of 1 minus x dx. What catches my eye right away is that I have 1 minus x inside of a square root, so I'm going to want to make that my substitution. So I'm going to let u equal the inside piece, which is 1 minus x. Then I'm going to find my du, which would be the derivative of that function up above, which would just be -1, and then times dx. So now we start trying to make our substitution. So in the bottom, I would have the square root of u. For the dx, I could put, let's see, we don't have a -1 in this, so if I come back down here, I could get rid of this -1 by dividing both sides by -1. So for the dx, I could put du over -1. The -1 I would just factor out front, and true, it's over -1, but multiplying by -1 and dividing by -1 have the same effect. And this would now be du. The problem is, I have some leftovers. I haven't handled that x, and I can't just write an x there. So what am I going to do about that? Well, I can take this substitution right here, and I can rearrange it and solve for x. If I add x to both sides, I get x plus u equals 1. And then if I subtract u from both sides, I get x equals 1 minus u. And now that x is the same as the x in our numerator, so I can substitute 1 minus u in its place. So that's what I'm going to do right here. What I just did there is referred to as a miscellaneous substitution. So you've done your u equals, you've done your du equals, you've done all of the substituting you can with that, but it looks like there's some leftover x values. Try to go back to your original substitution and solve for the x, and then use that to remove any remaining x's. All right, so that's the strategy. Let's see if that does us any good. So we have that negative out front. We have 1 minus u over u to the 1/2 if I rewrite that square root using fractional exponents. And then what I can do here, since we don't have a quotient rule, is I can split this up, make each one of those its own fraction. So this becomes the negative of 1 over u to the 1/2 minus u over u to the 1/2. And then I can reduce each one of these or rewrite them in a way where I can use the power rule. So this first piece becomes u to the -1/2. If I just bring that up to the top, its exponent changes signs. On the second one, I can just subtract exponents. So u to the 1 minus 1/2 becomes u to the 1/2. I still haven't found an antiderivative, so it's still an integral. All that was just trying to set it up for the power rule. But it is set up for the power rule now, so we'll use that. Add 1 to the power, so that -1/2 becomes +1/2 over 1/2, minus u to the add 1 to the power, so that becomes 3/2 over 3/2, and then we would have our plus c. And the only thing that remains to do is to simplify that a little bit and to get rid of the u's. So to get rid of the u, here and here, we just go back to this idea that u is 1 minus x. So let's go ahead and make that substitution. I'm also going to bring that 1/2 up as a reciprocal, so that becomes a -2, 1 minus x to the 1/2. That 3/2 I'll bring up as a reciprocal, so that becomes -2/3, 1 minus x to the 3/2, and then I have the plus c. And you can take the derivative and simplify this to verify that we have found a valid antiderivative. This one's a pretty good example of one where the substitution is really necessary. So is it possible that sometimes you could do these in your head without a substitution and it would be faster? Yes. Is this one of those? No. In fact, this is one I feel like we'd probably be completely stuck on if we didn't have this substitution technique with the miscellaneous substitution added in. It'd be very hard through trial and error to see what's going on, but the substitution path gives us more of a strategy to get through. And just separate this scratch work from my substitution off from the rest of the integral work. All right, let's go ahead and look at another one. So on this one, we have the integral of cosine squared d theta. And so Again, not necessary to do this, but this is the cosine of theta squared d theta. So we have what seems like a very natural substitution here. This is the inside piece. So we try that. We let u equal cosine of theta. And then we find our du by taking the derivative of the right-hand side, which is negative sine of theta, and then times d theta. And then we try to substitute. And at first it goes nice. You have cosine squared becomes u squared. But now you've still got this leftover d theta. So what are you going to do with that? Well, the temptation might be to come down here and divide both sides by negative sine theta. That does get d theta by itself, but the problem is it doesn't separate the variables. We've got a theta and a u on the same side. So if we were to make this substitution for d theta and put du over negative sine theta, we would not have completely switched our variables over. If you try and take this piece and solve for theta, that involves inverse trig functions, so that's very messy. So here's an example of where we try a substitution and it doesn't seem to get us in a better place. There are lots of integrals out there that can't be solved by substitution. Here's one of them. At least not by that substitution. So on this one, what we're going to do is do something a little bit more clever. We're going to use a trig identity. And the trig identity is that, let me adjust here. All right, the trig identity we're going to use is that cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2. So that's just an identity from trig. So that's not substitution in the sense of what we're learning right now, but it is a trig identity that we can use to rewrite this in a different way. So if we do that, this becomes the integral of 1 plus cosine of 2 theta all over 2 d theta. If you're wondering, like, why don't I take the derivative down here? Because I'm not actually changing variables, right? So this isn't a substitution in the traditional sense of what we've been doing up above. This is just using a trig identity to make some headway. Much like on the last problem, we can now split this into this part of the numerator over 2 and then this part of the numerator over 2. So split it into two separate fractions. So we have 1/2 plus the cosine of 2 theta over 2 d theta. So now we just take the antiderivative of each of these pieces. So the antiderivative of the 1/2 is 1/2 times whatever the variable was, in this case theta. That 2 in the denominator, let me just pull that out front as a 1/2, and then the antiderivative of cosine would be sine. But if it's 2 theta, then we have to divide that by 2 because of the chain rule, and then plus c. So we end up with 1/2 theta plus 1/4 times the sine of 2 theta plus c. So that would be my final answer for this one. And we can kind of check that one by taking the derivative, but it won't take us all the way back to the original. It'll just take us back to this spot right here. But still worth a quick check. So let's check our work real quick. The green part's our answer, but taking the derivative of it with respect to theta, the 1/2 theta becomes 1/2. We have the 1/4. We take the derivative of sine, which is cosine of 2 theta, but then by the chain rule, we have to multiply by the 2 from the inside function's derivative. Derivative of the constant would be 0. This 2 cancels that 2, gives us a 2. And out front, we have our 1/2. And after that, we have cosine of 2 theta over 2, which is this piece. So we can't go all the way back unless we make a trig substitution again. But we can see that after we made the substitution, the work from there was a correct antiderivative. All right, continuing on with substitutions, but now we're going to look at it in the context of a definite integral. So let u equal g of x, where g prime of x is continuous on an interval, and let f be continuous on the range of g. Then if you're doing the definite integral of f of g of x times g prime of x dx, you can make a substitution where u equals the inside function g of x to get f of u du, just like we did before. But the thing that's going to be different now is we have to remember to also substitute for our limits of integration. So if you remember what I said before, we need to completely switch variables. So we have to switch over from x to u. Well, this a and b, that's x is going from a to b. So if we're going to make a substitution to u, we need to know what is u going from. And we find those values by just plugging the a and the b into this u substitution formula. So a few notes about this, then we'll look at some examples. The first note is you must use your u substitution to change the limits of integration. So that's the part I was just talking about. And then the second note is you never need to switch back to the original variable. So that's a surprising piece for people, and one that they often fight against a little bit. But because you're changing the limits of integration, you can now plug those limits of integration into the u answer of your definite integral, and it will give you the correct answer for the original. So let's go ahead and look at the process through an example. I think we have a fairly clear inside function here. 2x plus 6 is inside of this fourth power. So we're going to let u equal 2x plus 6. So du will be the derivative of that, which is 2 times dx. If we look at our leftovers, it's just dx, not 2 dx. So I would divide both sides by 2 to get that dx piece by itself. So in place of the dx, we're going to end up substituting du over 2. So we're going to do that, but at the same time, we have to think about the limits of integration. So an extra piece to our substitution. So what happens to u if you plug a negative 3 in for x? Not picking that negative 3 out of thin air. That was our lower limit of integration. Now I'm plugging that into the x spot to see what that becomes in terms of the new variable u. So 2 times negative 3 is negative 6, plus 6 is 0. So that will be our new lower limit of integration. So how about the upper limit of integration? You plug the 0 in and get 2 times 0 plus 6. So 6 is going to be our new upper limit of integration. So I end up with the integral from 0 to 6 of u to the fourth, and then in place of the dx, du over 2. So there's the du, there's the over 2 out front. So a complete substitution of variables. Every part that was an x is now written in terms of u, and that has to include the limits of integration. From here, it's pretty easy to finish off. The 1/2 we'll leave alone. Antiderivative of u to the fourth, we just get to use the power rule, so u to the fifth over 5. We don't have to do the plus c when we're doing definite integrals, but we do have to plug in the limits of integration. That 1/2 in the over 5 is a 1/10. I'm going to just pull that out front. And then plug the 6 into the u to the fifth, so that'll be 6 to the fifth minus 0 to the fifth, which of course will just be a 0. So we just end up with 6 to the fifth, whatever that is, and it turns out 6 to the fifth is 7,776 all over 10. Not a whole lot you can do with this, but they both are even, so you can cancel a 2 in the top and the bottom, and you end up with 3,888 over 5, which does turn out to be 777.6. So which answer should you give? It depends on the directions. Since I didn't get any directions here directing me to convert my answer to a decimal, I'm going to highlight that fraction so that I'm giving an exact answer. All right, so again, key things. We had to change our limits of integration as part of the substitution. So we switched from negative 3 to 0 to 0 to 6. Here was my lower limit of integration substitution because I plugged the negative 3 into the u substitution. Then the upper limit was 0, so I plugged that in. So that 6 became the upper limit. That's one key thing. Don't forget to change your limits of integration. But then the nice thing at the end is no need to backward substitute. So there's our final answer without ever going back to x. All right, even though we are in fact done with this, I want to go ahead and just show you one quick thing, which is what if we did back substitute? I think it's kind of a waste of time to do in general, but a lot of times people feel very uncomfortable with this idea that we never went back to x. So let's take this part of our answer and let's back substitute right there. So we have 1/10 u to the 6th, is that right? 1/10 u to the 5th. And it's evaluated from 0 to 6. So let's back substitute now. So we have 1/10, and then what was u? U was 2x plus 6. Because we switched back to x, we would have to switch back to our original limits of integration, which were -3 and 0. We could factor the 1/10 out front. We could plug in the 0. So when we plug in the 0, this part goes away, and we just end up with the 6. Sorry, this was to the 5th power from right here. So we end up with 6 to the 5th power minus, and then we plug the -3 in, and 2 times -3 is -6, plus 6 is 0. So we end up with 0 to the 5th power. And notice that's the same thing that we had up above, right? That's right where we were right there. So of course the answer is going to come out the same. So could you back substitute and put in the x? Yes, but it's extra work that doesn't change the answer. So I would recommend that you not do that. It's kind of a waste of time. Just go back, and after you have substituted, after you found the antiderivative, because you've changed your limits of integration, you just change those new variables. So other things sometimes people will do is say, well, how about if I just leave the limits of integration alone and then I substitute? But then in the middle, you don't have something that is correct. If you write this integral right here that I just underlined with the old limits of -3 to 0, and you say evaluated that definite integral on a computer, you will not get the correct answer there because you have the wrong limits of integration. So when you switch over to u, you have to do that to every part, including the limits. Takes a little getting used to, but we've got some more examples on the next page. All right, let's get some more practice with this. We're going to look at the definite integral from 0 to 7 of the square root of 4 plus 3x dx. I think we have a fairly obvious inside function again. We have 4 plus 3x inside of the square root. So I'm going to let u equal 4 plus 3x. Got a little messy, just clean that up. 4 plus 3x. And then du will be the derivative of that, which is just a 3, times dx. When we look up at the top, the only leftover pieces after we substitute and get a square root of u would be just the dx, so this piece. So I don't want that 3. So I'm going to divide both sides by 3. And that will complete the substitution. It's going to be the square root of u times du over 3. It'll complete the substitution, that is, for everything but the limits of integration. So let's do the top limit first, just so they're kind of in order here. So we'll plug the 7 in. So u equals 4 plus 3 times 7. And then, so that's our upper limit. And our lower limit will be 4 plus 3 times 0. So 4 plus 0 is 4. 4 plus 21 is 25. So our new limits of integration in terms of the new variable u will be that we're integrating from 4 to 25. All right, so that's all kind of our scratch work to make the substitution go. So let's work from there. We have the integral now from 4 to 25. Now the square root of u. And in place of dx, we will put du over 3. So here's the du. There's the over 3 out front. You can put the over 3 like right there where the du is, but the next step would be to factor it out. So I always like to just do that ahead of time. And then we have 1/3 integral from 4 to 25 of u to the 1/2, rewriting it as a power so that I can apply the power rule. So 1/3 times u to the new power, which would be 1 higher, so 3/2, divided by 3/2, or out front times the reciprocal of 3/2, which would be the 2/3. And no plus c, because it's a definite integral. Our limits are from 4 to 25. So out front, looks like we have 2/9, and then times plug in the 25. That would be the square root of 25. That's the over 2 part, raised to the third. So you can see my 3 and my halves. The 3 is the exponent, the 2 is the square root. And then minus the same thing with the 4. So the square root of 4 raised to the third. So where does that take us? 2/9 times 5 to the third, which is 125, minus the square root of 4 is 2. 2 to the third is an 8. So we have 2/9 times 125 minus 8, which, if you do the math on that, turns out to be 234 over 9. And 9 goes into 234 26 times. So we end up with a nice clean answer of 26. So there we go. So again, making the substitution, make sure you do a complete substitution. So plug in the 0 and 7 so that you get new limits of integration now in terms of the new variable. So those become 4 and 25 instead of the previous ones of 0 and 7. But after you find your antiderivative, you go straight to substituting in those limits of integration that correspond to that variable, which are the u versions, the 4 and the 25. No need to ever go back to the x variable. All right, on to another example. We're doing the definite integral from 1 to 2 of x squared over x cubed plus 1 squared with respect to x. Looks like a messy one for trial and error. Good thing that's not our technique. We're going to let u equal that inside piece. When you have something raised to a power, when you have stuff raised to a power, it's almost always the case that that should be your u substitution. So u equals 3x plus 1. Sorry, I think I was starting to take a derivative in my head there. U equals x cubed plus 1. And then du will be the derivative, 3x squared times dx. Now let's look at what's left over. If you substitute for what I have in yellow already, you would still have this x squared and that 2x. That's this x squared and that dx. I think I might have said 2x. So now to get that piece by itself, we divide both sides by 3. Those 3's cancel, and x squared dx is du over 3. But to do a complete substitution, we also need to do the limits. So for the upper limit, we would plug in the 2 and get 2 cubed plus 1. For the lower limit, we would plug in the 1 and get 1 cubed plus 1. So 8 plus 1, 9, 1 plus 1, 2. So just focusing on those limits, there's the 2 for the upper, so I plug that in for the x in my substitution. There's the 1 for the lower, so I plug that in for the x in my substitution. All right, so that is going to get us a complete switch from x to u. So let's rewrite it. We have the integral now from 2 to 9. On the bottom, we have u squared. And then the top and the dx is the x squared dx in green. Looking down here, the x squared dx is du over 3. So I'll put the du here. I'll put the over 3 out front. I ended up with nothing in my numerator, so I'll put a 1. And then we just do our antiderivative work. So 1/3, the definite integral from 2 to 9. This is going to be u to the negative 2. That's now set up to use the power rule. So I have the 1/3. Use the power rule, add 1 to the power becomes negative 1. Divide by the new power, negative 1. Evaluate that from 2 to 9. No plus c on definite integrals. So just simplifying a little bit, we have negative 1/3 times 1 over u evaluated from 2 to 9. I'll just leave that negative 1/3 out front. Plug in the 9, we get 1/9. Plug in the 2, we get minus 1/2. This looks like a good one to go ahead and use our cheater skills on the calculator. So you could do the common denominator work and all that, fine. But I'm going to go ahead and just punch it in. So negative 1 divided by 3 times 1 divided by 9 minus 1 divided by 2. There's my answer as a decimal. Math, store fraction, enter. Looks like it's 7/54. So go ahead and switch back. Equals 7/54, final answer. All right, on to the next page. All right, we're going to finish up with an example of the use substitution on a definite integral for trig functions, and then one that involves a miscellaneous substitution. So let's go ahead and get to work on this one. So the first thing I'm going to do is just that kind of rewrite to make things a little bit easier for us to see. So we're doing the definite integral from pi/4 to pi/2 of cosine of x, and it says sine squared, but just a reminder that that means sine of x squared dx. So I like writing it that way just so that it's clear that our inside function is sine of x. So now I'm going to let my substitution be u equals that inside piece. So u equals sine of x. So for du, we take the derivative of the right-hand side, which is cosine of x. We tack on the times dx. And that looks like that's going to be a nice cleanup of the leftover pieces. Cosine x dx is the leftovers. Cosine x dx is what I got here. So that's just going to be a clean substitution of du. We just have to remember to substitute for the limits of integration as well. So for our upper limit, it'll be sine of the old upper limit, so sine of pi/2. For our lower limit, it'll be u equals sine of our old lower limit, which was pi/4. So just thinking about unit circle, so you can do that over here. So sine of pi/2, that's the y-coordinate at the top of the unit circle. That's going to be a 1. And at pi/4, that's right in the middle. That's the spot where both sine and cosine are equal to √2/2. So that's going to become my new lower limit of integration. So there's all the scratch work. Just a quick note, by the way, on these limits of integration pieces. I've been writing them down to help you kind of see what's going on, that I'm substituting these old values into my u substitution. But you don't have to do that if you can do it in your head on the fly. I was looking at my old notes and I didn't write that down. I just thought, like, I just did it on the fly in the sense of saying my old limit was pi/4. What's the sine of pi/4? √2/2, and I just wrote it down in the definite integral. So whether you write it like we did right here or not is kind of up to you. But I would do that at first, at least, while you're getting used to it. Once you start feeling like you really got the process down, maybe you don't need that anymore. All right, so our new limits of integration are going to be a lower limit of √2/2, upper limit of 1. In place of the sine x, we're going to have a u. So on the bottom, we're going to have u squared. In place of the cosine x dx, we just get du. So I'll put a 1 up top as just a placeholder. And then √2/2 to 1 of u to the -2. So then I can apply the power rule. That's going to be u to the -1 over -1, evaluated from √2/2 to 1. That is a -1 over u, evaluated from √2/2 to 2 to 1. So moving the negative out front, we have 1 over the upper limit minus 1 over the lower limit, which would mean we'd get a reciprocal of √2/2, so that'll become 2 over √2. And then you can rationalize that, multiplying top and bottom by root 2. And if you do that, you'll get 2 root 2 over 2, and the 2's would cancel. So this part right here, root 2 times root 2 is just 2, so that'll cancel this part, and you get just the minus root 2. So I don't have much room to write, so let's do a little work in our head. Where are we? Inside parentheses, we have 1 minus root 2. And then out front of that, we have a negative. So let's just distribute that negative in and say it's negative 1 plus root 2, and that will be our final answer. Not going to a decimal because they didn't ask me to, so giving an exact answer. All right, one more. Let's go ahead and take a look at one that involves the need for miscellaneous substitution. So inside piece, inside the square root, I have a t plus 1, so that seems like the most obvious substitution, so I'm going to let u equal t plus 1. Take the derivative, so du is equal to the derivative of t, which is 1, times du, so dt. And then, so that means du equals dt. If we were to make the substitution du equals dt, that would take care of that piece, but we still have that 3t to deal with. So we could deal with the 3 easy enough. We could multiply both sides by 3 and get 3 du equals 3 dt, but we still would have that t out front. So what do we do about that? A miscellaneous substitution. Subtract 1 from both sides and you get u minus 1 equals t, and we can use that t right there for that t right there. Okay, so there's all the scratch work. I'll go ahead and do the limits of integration on the fly this time, just since I talked about that before, so you can see what does that look like. So we're going to do the integral was from 0 to 3. Put a 0 in there, and you get u equals 0 plus 1, so your new limit of integration is a 1. Now plug the 3 in for that t, you get u equals 3 plus 1, so your new upper limit of integration is 4. So a lot of times it's easy to do that substitution of the limits on the fly, so feel free to do that if you're comfortable with it. Feel free to write it down like I've been doing if that helps you, but you have to make the change in variable applied to the limits of integration. All right, on to the inside. I'm going to start with this t right here out front and use my miscellaneous substitution, which is t equals u minus 1. That's this piece down here. For the square root of t plus 1, that'll just be the square root of u, and the 3 dt will be 3 du. I'll move the 3 out front, put the du right there. I'd like to take an antiderivative right away, but I've got a product, so we're going to use the product rule. Sorry, we would use a product rule if we had one. We don't, so we're not going to use the product rule. We're going to distribute instead. So 3 times the definite integral from 1 to 4, that square root of u is a u to the 1/2. So u to the 1/2 times u becomes u to the 3/2, minus 1 times u to the 1/2 is u to the 1/2. Then we have the du. So now we have this set up to be able to just use the power rule. So leave that 3 out front. This becomes u to the 5/2 over 5/2, or times 5, over 5/2, or times 2 over 5, doing the reciprocal, minus u to the 3/2 over 3/2, or times 2/3 if I do the reciprocal. No need for the plus c. There is a need to evaluate. We're evaluating from 1 to 4. So a little bit messy. Let's see if we can attack this. So first the 4. Plugging the 4 in to this piece right here. The 2 is a square root, so the square root of 4 is 2. 2 to the 5th is 32. So we end up with 2 times 32 over 5 minus 2/3 times. Now we're going to plug the 4 in here, take its square root, which is 2, raise that to the 3rd, which would be 8. So times 8. And then, let's put that in parentheses. That's what we get when we plug in the 4. minus, what about if we plug in the 1? That's a little easier because 1 to any power is still 1, so we just get 2/5 minus 2/3. And then I think from there, we could just go ahead and plug that into the calculator. I actually did that, and it comes out as a nice number. It comes out to be 23.2. So that 23.2 would be our final answer. Yes, it's a decimal. If you don't like that, that's 23 1/5. So we can convert that to a fraction if that's what they really want. Not so bad to switch to a decimal when you're not rounding. If you round it, you're bringing in error. But if you get an exact decimal, it's not such a bad thing to switch to a decimal there. All right, that wraps up section 5.5.